Hello everyone, in this video we're going to go over the solutions for the week 8 worksheet. So in this week we have alternating series, and we also check the absolute convergence notion. So first, the first three exercises, we're trying to determine if the series converge, diverge by using alternating series test. So the alternating series test is just a reminder. We consider that the sequence that we have is a function, and then that function is decreasing. And also we're checking that the limit when n goes to infinity of an is 0. And if these two things happen, then we can say that the series of the alternating series is convergent. Okay, so we can write this series here as like -1 to the n an, and this converges. Okay. So this is what we're going to use here. So for the first scenario, notice that we have the series from n equals 1 to infinity of -1 to the n plus 1 over 1 over n plus 1. So essentially we have that f of n is 1 over n plus 1. One way to prove that this is decreasing is to show that the term an plus 1 is actually smaller than the term an. So if we show this for all n, then this shows that it's decreasing. We can easily do that here because n plus 1 is just bigger than n, and then 1 over n plus 1, sorry, there will be n plus 2. So n plus 2, because the sequence is n plus 1. So n plus 2 will be the n plus 1 term, and n plus 1 will be the an term. Hopefully that's not confusing. So we have that 1 over n plus 2 is less than 1 over n plus 1, and so that means that the term an plus 1 is less than the term an, and so an is decreasing. We also have clearly here that the limit when n goes to infinity of 1 over n plus 1 is 0. And so by alternating series test, we have that the series from n equals 1, from -1 to the n plus 1, 1 over n plus 1, then converges. Now the next exercise is the series from n equals 1 to infinity of -1 to the n plus 1 times n squared divided by n cubed plus 1. So clearly here an, consider our function, is n squared over n cubed plus 1. Notice that we can very easily know that this limit is actually going to infinity, sorry, to 0, when n goes to infinity, because just the power of the denominator is bigger than the numerator. This is an infinity over infinity limit, but we can use like L'Hopital's rule. And this is just going to be 2n, and then here is just going to be 3n squared. L'Hopital's rule, again, is going to give me limit when n goes to infinity of 2 over 6n, and that's just 0. Remember L'Hopital's rule is what we're using here, since this is infinity over infinity in determinant form. So we have the first part of the alternating series test. Also, if we want to try and see that this is decreasing, will be fairly complicated to compare the n plus 1 term with the an term. So instead, I'm just going to do the derivative. So f prime here is just going to be 2n times n cubed plus 1 minus n squared times 3n squared over n cubed plus 1 squared. Of course, to realize that this is negative like we expect, we need to simplify. So this is 2n to the 4 plus 2n, and then minus, and then we have here 3n to the 4. Now we can kind of see where this is going now at this point, because we're going to have that this is 2n minus n to the 4th. And the denominator is something that is always going to be positive, but if n is large, then this is going to be negative, and that implies that f is decreasing. And so by consequence, by alternating series tests, we have that the series from -1 to the n plus 1, n squared over n cubed plus 1, from n equals 1 to infinity, converges. Now, the last one from this first batch, we have the series from n equals 0 from -1 to the n, 1 over n to the 1/2. So I'm going to assume really that this is from n equals 1, since it cannot start from 0 because of the denominator. Otherwise, this just will be divergence here. So we're going to start with assume that it's from n equals 1. Notice that the limit when n goes to infinity of 1 over n to the 1/2, this is like 1 over square root of n. This is 0. Very easily we can see that. We can actually use the decreasing argument here because we know that n plus 1 is bigger than n. And so we know that the square root of n plus 1 is actually bigger than the square root of n. And this is equivalent to n to the 1/2 being less than n plus 1 to the 1/2. And so this means that 1 over n plus 1 to the 1/2 is less than 1 over n to the 1/2. And so we have that the term an plus 1 is less than the term an. And so an is decreasing. So again, by alternating series tests, then we can claim that the series from n equals 1 to infinity of -1 to the n, 1 over n to the 1/2 converges. Okay, and so this is the end of the alternating series test on the question number 1. Now let's go to question number 2. In question number 2, we're trying to say to know if the series that we have converges absolutely, conditionally, or diverges. So for the first one, because we want to try conditional convergence, absolute convergency, then we're gonna kind of check what happens with the absolute value of the series. So this is like -1 to the n over n squared plus 3. And so the absolute value is just going to be the series 1 over n squared plus 3. And there are multiple ways that I can approach this. One of them is just by the fact that n squared plus 3 is bigger than n squared. And so by that, by comparison criteria, we're going to have that this happens. We're going to have that 1 over n squared is actually, the series of 1 over n squared is actually bigger than the one from 1 n squared plus 3. And so now since this one is convergent, then by comparison criteria, this one converges. And we can kind of say that really this one converge absolutely. Notice that if necessary, if you're writing, you might want to write this one and prove that it converges. And you can say this converges by integral test, being a p series with p bigger than 1. Okay, and that's a good argument for this. Now, question B is very similar as well. We can kind of do the absolute value, and the thing when we do the absolute value is that we're going to see that it's very close to the harmonic series. So we have -1 to the n over 2n plus 1. that series is just essentially the series of 1 over 2 plus 1. And now I can do a little bit of condition. I have 1 over 2n plus 1. And I can simply say, well, this is going to be less than 3n. And so 1 over 2n plus 1 is bigger than 1 over 3n. And so this will be bigger than the series of 1 over 3n, which can be 1 over 3 series of 1 over n. And this is the harmonic series that diverges. And then again, by comparison criteria, we're going to have that 1 over 2n plus 1 diverges. So we do not have absolute convergency here. However, we can check that indeed limit when n goes to infinity of 1 over 2n plus 1 is equal to 0. And we can check very easily that 1 over 2n plus 1 is a decreasing series, is a decreasing sequence. So by alternating series tests, we have that this series is going to converge conditionally. So this converges conditionally. And that pretty much is giving me one example of each. So I have one example where it was absolutely convergent. In this case, it's not absolutely convergent, and you find that it is actually converging conditionally. Let's look at the last example for today. And it's the series from n equals 1 to infinity of minus 1 to the n over n cubed plus phi n. So my gut feeling is that this is going to be something that is convergent, just because this probably can be compared with a p-series. So let's take a look at that. N equals 1 to infinity of absolute value of that is going to be equals to and the series for n equals 1 to infinity of 1 over n cubed plus phi n. And so now n cubed plus phi n is going to be actually less than n to the 4. When n is bigger, this is going to be less than this. Oh well, I need actually something that is bigger than this, so this is not going to be useful. Let's just use n cubed. This is just bigger than n cubed, and so because it's bigger than n cubed, we have that 1 over n cubed plus phi n is less than 1 over n cubed. And so this implies that this is less than this series 1n to the cube. And now, because this is a p series, p bigger than 1 series, converges by integral tests. And so that implies that by comparison, we have that the series of minus 1 to the n over n squared plus phi n converges absolutely. So at the end of the day, when we're trying to find something is absolutely convergent, we check for what happens with the series of the actual value. But if the series of the actual value is divergent, we still gotta check the alternating series to see if the alternating series by itself is convergent. So we can kind of say, oh, okay, so this at least is gonna be conditionally convergent. Otherwise, then we gotta try and prove divergency. Okay? So that is the end of week 8 worksheets.